Thank you. Sorry. So my name is Jorge Olivar from Agresta, and I'm here to present you the baseline of soil organic carbon in mining areas. This work is part of a live project that we just started. The project is called Carbon to Mine, and just started on last October, and it will last 6 years. The general goal of the project is to increase carbon sequestration from soils and vegetation to contribute to climate change mitigation. The study area of the project are the Asturian mining basins, which is one of the most economically depressed regions in Europe and are directly affected by the European decarbonization projects. And the project is bigger than this, but if we focus on our task, the expected results that we have in relation to our task is to maximize carbon fixation in forest sinks, and for those areas that are not forested, to restore these degraded mining areas to improve the sequestration capacity. This is part of the work package number 5, which is called Monitoring and Evaluation of Sustainable Management Models. And our goal is to develop a monitoring tool for the pools in the study area at a regional level. And for that reason, we will develop a digital soil carbon map of the study area. So this is very important, that this is not something that we have already done, but it's something that we are going to do. So what I'm going to present you here is the general idea, the methodological workflow, and I hope in some months or in some years I will show you the first results. So to begin with, we have some baseline data. On the one hand, we have soil databases that are based on point information, and on the other hand, we have soil maps that are based on polygon information. For the ones based on point information, as you know, we need to make an additional process, which is to go from the points to continuous data. Specifically, in our study area, we don't have many available points. For this process, to go from the point information to spatial information, we need these spatial interpolation techniques and representation. And we can go for the machine learning technique, there are many examples that use that technique, or the geostatistic technique. There are also national maps that are based on these techniques. But the problem that we saw from the beginning is that if we compare soil organic carbon maps this is not our study area, but it is one that is very similar, with similar characteristics, very degraded soils. And we can see how the values are quite different and the resolution is also quite different. So therefore, we thought that it's necessary to create a local soil organic carbon map, and this is where the artificial intelligence is interesting for us. This integration of the artificial intelligence in soil organic carbon mapping has many opportunities. For example, the accuracy of the soil organic carbon map estimates has improved as a result of the development of the digital soil mapping technologies, which is something that we will implement. And this digital soil mapping offers the possibility of using a huge amount of digital resources, in our case something between 100 and 300 predictors, that could be included in these soil organic carbon models. It is important that the relationship between the soil properties and the environmental variables are usually complex and non-linear, especially in degraded soils and especially if you don't have many samples. So we will adapt techniques from data mining, machine learning, multimodal ensemble methods to detect these complex patterns in the large data. And these techniques will improve the digital soil mapping predictive capacity to provide the spatially continuous information, which is what we need to have a map with continuous information. And very important, the uncertainty of the maps. However, we have some opportunities, but we also have some risks. First of all, this high variability of soil organic carbon requires intensive soil survey, which is expensive, complex, difficult to replicate. So the use of machine learning, if the area is undersampled, could produce overfitting for the modeling. This low sample, in contrast with the many predictors, can lead to spurious data model agreements and could be influenced by over-parametrization. There is also a difficulty to interpret the covariates influencing soil carbon models. So we have a risk of having statistical redundancy. And due to this variability in the validation methods, the model evaluation metrics are difficult to compare. So having all of this in mind, our methodological workflow will be based on 3 steps. In general, for the first step, we will gather national and regional soil profiles and standardize and merge all these profiles, and gather remote sensing data repositories based on biological or environmental variables. The second step will be to use machine learning and modeling to see the influence of these variables on soil properties. And the third step will be to compare and evaluate all these methods and make a validation of our predictions. If we go more into detail, the first step, we will focus on digital soil mapping. As I mentioned before, is going from soil organic carbon samples to spatially continuous spatial information. So we will upscale the information that we have from the points to a continuous map. For this part, we will use the Scorpan technique, which is based on environmental covariates, and the general idea is that there is a relationship between these environmental covariates and the soil properties. As a second step, we have to choose the right environmental variables. So we will use, for the future selection, we will use multiple linear regression, Bayesian analysis, and projection pursuit regression. For the second step of the methodology, we will use machine learning models, like QBIS and random forest. We will also use quantile regression forests, and the idea is that the resulting models that we will display, the idea is that they display the most likely value of the response variable of the soil organic carbon. But since we will have the models, we have to assess the accuracy of this model, which is also very important. So for this, we will use the concordance correlation coefficient and the normalized RMSE. In this part, we have to take in mind that smaller differences from both the calibration and the validation datasets imply better robustness and no overfitting. We will also use nonparametric regression curving technique, but we have to be careful because with a low density and cluster distribution of the soil data, which is the case, this additional curving of residuals is not recommended. And the last part is that we will create the spatial prediction maps, but we have to balance between the spatial resolution and the uncertainty. In this case, it's quite logical that as we increase the number of predictions, the level of uncertainty decreases. So our idea is to have a high amount of predictions in order to decrease this uncertainty. So having all this in mind, our further steps for this project will be to generate a cost-effective, high-resolution map of soil organic carbon distribution, the associated spatially explicit uncertainty, and to do this at a management scale. And this is important because this baseline soil organic carbon map will be valuable for modeling carbon storage changes and their different management practices. So this is what we will do in the following years. And hopefully I will show you at some point. Thank you.